All right, up and running. So my goals today, this is pretty much yesterday's, we had that quiz yesterday, so we started a little bit late. So this is the 2.2 lesson that I didn't identify it, but we started talking about limits. If you looked at the schedule, you probably noticed that there was no lesson 2.1. That doesn't mean it's a bad lesson. It's a way of interfacing between algebra and calculus, and right at the intersection of algebra and calculus, kind of wedged in between and helps us make the bridge, is the concept of limits. So the next lesson, and it's the one we were working on yesterday, was lesson 2.2, finding limits graphically and numerically. So in your book, it's lesson 2.2, and you'll notice on the schedule, on the schedule, you'll notice that it doesn't have a 2.1. So this is what the function we started with yesterday. And remember, we were just looking at what happens as the values increase, in this case, get closer and closer to 2. So in this area right here, you can see as the values of x, we were approaching 2 from the left. So that's what was going on right here. And we learned that new limit notation. Limit as x approaches 2. As we were approaching 2 from the left, the function looks like it was approaching 7. And then we noticed that as we approached 2 from the right, again, the function seemed to be approaching 7. And then we learned an important truth here by the green arrow, that when a left and a right hand limit approaching the same number from the left and the right agree, then we say the limit of the function as x approaches 2, there's no sign here, as x approaches 2 is 7. So when you have a limit with no little plus or minus here, saying we check that out from both directions. And then it's kind of interesting to note that in this case, not only does the limit of the function approach 2, but you actually find the value of the function at 2. It's, you notice these are the same. Yeah, so this is pretty straightforward. But not all functions are like this. Also, we know that you can also approach it by looking at the graph itself. So, in Desmos here's actually where I created this. You can see that nothing weird. Why I am muted. Can you guys hear me?
Yeah, you're good now.
Now you can. Thank you. I apologize. I don't know how that. It's interesting. It said James muted me, and well, anyway, we're on. I believe just one more time. I got a note from David. Anybody? Your audio cut out. How are we doing? Can everybody hear me? I got an okay from David. Let me just get one or two more.
I can hear you.
I can hear you.
All good here.
John is back in. I see some of you may have tried to come out. Anybody else? I
Yeah.
just want to get an indicator. Are you hearing me?
Yes.
Yes.
I'm hearing you.
You can unmute your mic and tell me too.
Yeah,
I just want to get a couple. I just want to make sure we're being successful here.
I just
Yeah, I can
lost
hear.
connection from the.
Anyone
Hang on
else
for a second.
besides David? Can you guys hear me?
Yes, I can.
I can as well.
I also can.
Yes, I can.
Okay, good. So we're up. I'm sorry about that. I may have accidentally clicked mute. So anyway, we were talking about the fact that this first function we talked about yesterday, the limit as x approaches 2 was the same as f of 2. That's because this is a nice behaving function. I mean, there's no gaps, there's no jumps, there's no division. Well, there could be a problem with division by 0 if you look at the function over here on the left. In other words, at x equals 1, we would have a problem. You see that? Because if x was 1, the denominator would be 0, and we'd be up the creek. But notice we're not dealing with 1. We're dealing with as x approaches 2. So at least at the point we're discussing it, we're good. Okay, so that's why that happened. So then when we went to the second function yesterday, was this nice polynomial. You can see just by looking at x squared minus 4x plus 3, I mean, we don't have any problems there. That's just a good old straight polynomial. And here we switch the graph. No, I got the wrong one. Hang on. Yeah. So when I switched to this graph again, it looks pretty normal. We can see algebraically x is never going to run into trouble. So what happens then when we take our limits? Again, we look here as x is approaching 2 from the left. This seems to be approaching -1. And this time I did it, yeah, I don't know, kind of a strange approach here. But as we approached 2 from the right, again, we approached -1, and no shock, these two agree again. The actual value at -1 is the same as its limit, but not all functions will do that. Okay, so let's go yesterday when we did the third function we looked at. Now we have kind of a unique thing going on here. We've got this x in the denominator, and we're checking the limit as x approaches 0. Now we have a problem. We would have, and you can see it right down here, undefined. So do you see how these two do not agree? The limit as x approaches 0 from the left and the right is 4, but that's not equal to the value of the function at 0. So we've got, and you can see it on my chart too. I included it over here. Okay, so you can see we've got different possibilities here, and let me change to that function on that's part B. Yeah, you can't see it real well here, but you can see some unique things are going on with this function, and you can't see it. Let's see if I zoom in. You still can't see it because we just can't tell what's going on as x approaches 0. But we know you cannot plug in 0. I mean, The sine of 0 is legit. The sine of 0 is 0, but and so 0 times 4 is 0, sine of 0 is 0, but you can't divide by 0. So you can't see it on the graph, but we've got a hole there. And you can see it on you can certainly see it when we come back and look down here. All right. So here, the left and the right-hand limits agree, but that doesn't equal what the function does. Okay. So now is where we're going to move on now. We're going to do this part C. And you can probably tell we're approaching 0 over here. So as we do some writing here, we want to find the limit as x approaches 0. And the first time we're showing it what? As it approaches 0 from the left. And what does it look like? It's just -5, right? And notice this didn't even change. Okay, let me move this down and let's look at the right-hand limit. So the right-hand limit, this time we're in the positive range, and actually we're going this way, aren't we, this time? Sorry, I was inconsistent with that. But the limit as x approaches 0 from the right, this time is, oh, they don't agree. You see that? So we've got these things don't even meet. So here's the first time we see that the left and the right-hand limits do not agree. And now, if we take away, if we just say as x approaches 0, what's the overall limit? Because these two do not agree, I mean, different books do different things. They often will put DNE for does not exist. Okay? So here's the first time we've seen this. We've got limits that don't agree. And you can't have that. So we say there is no limit, or we say it does not exist, DNE. And you can see there's also a problem at 0. I mean, I haven't done it yet, but what is f of 0? It's undefined. You can't divide by 0. So this, we don't have any limit here at all. Let me just see, what do I have for a function here? So this is C. Yeah, let me zoom out a little bit. And you can't see it completely, but you see how on one side it's approaching, on the negative side, it's down here at -5, and on the positive side, it's up here at +5. And there should be what? An open, you can't see it, but there should be an open dot right on the x equals 0, right on the y-axis. So these two guys whiff. They don't meet. And that's what it looks like graphically. Okay. Now let's go at the next function. Okay, so this is different. We've got 1 plus, yeah, here, let me also get the graph up. So this is part D. So here's what this thing looks like when you show it graphically. And you can tell by the ordered pairs that we're approaching what? We're approaching 0 from the left, right here. Okay. So the first thing we're going to note here is the limit of f of x as x approaches 0 from the left. And I mean, we don't know any rational thing, but it looks like it's approaching what? I don't know, 1.6487 is all we know from the decimals here. And then when we check it from the right, and again, I'm going the opposite way this time. So as the limit, as x approaches 0 from the right, appears to be the same thing that was from the left. Okay, so these are in agreement. Therefore, it appears that the limit, as x approaches 0, overall, it's about 1.6487. Okay, but then, what's f of 0? And you'll see, do you see why it's undefined? It's because in that exponent, you see, if you look right up here, in that exponent, you see that we had 1 over x, and if x is 0, you've got a 0 in an exponent denominator. That's exponent is garbage, and so this is true. Despite that, we have a legitimate limit. So even though there's a hole at 0, which again you can't see here on this graph, you can see that it's still, these don't whiff. The two sides of the graph from the left and the right are still coming at the same place. So we have a limit, even though we have a hole there. So it's important that you, and these lab exercises were designed to kind of expose different scenarios that come up. Okay, so that's yet different. Okay, so that's part D. Let's go on to the, by the way, you guys speak up if you want, if you don't get something that I say, and hopefully you can still hear me. All right, so let's go on to the next one. And here's our next function. This is E. Let me load one up here. Okay, you can see we have kind of, you can see where I think you can see where the influence of the sign comes in. Where the influence of the sign comes in here, the S-I-N-E sign. You can see the waviness of the sign, but then what happens as we get closer to the y-axis, you can see this thing from the left side heads for negative infinity, and from the right side it seems to go up to positive infinity. You can just see that visually. So now as we look at this, how can we express that? You can see as we approach 0 from the left, it appears that, by the way, some books would say there is no limit. Do you see how huge this is? Look, we go from negative 39, negative 400, negative 4,000, negative 40,000, and then it just keeps shooting. It's going to negative infinity. In other words, some people would say there's no limit, but you'll hear we're going to be speaking of that as it's heading downward big time, okay? So we say negative infinity. And then what happens, you already saw it on the graph, what happens when you approach 0 from the right? So we're now, as the values come up, you can see that the right-hand limit, as x approaches 0 from the right, and now it's firing upward at incredible rates. We're at what, 400,000 here? So now it's heading for positive infinity. And because these two don't agree, the limit as x approaches 0 in general, it doesn't exist. So it does not exist. There is no limit And you could have seen that on the graph. Hey, the two ends don't meet. There's a major whiff here. The two sides of the graph do not meet. Okay, so we've got another scenario. Okay, now let's look at the next one. You can see we have a polynomial, but we have a denominator. And right away, your domain experience should shoot up. Wow, x can't be 3. So we have a problem here when it comes to that. Okay, let me load up F here on the graph side. And I gotta zoom out here so you guys can see more completely. So this is what this thing looks like. We've got these two branches of the graph that are not meeting. And at x equals 3, you can see there's a vertical asymptote. You guys are familiar with that from algebra class. All right, so now let's go back to this. So as x is approaching 3, and this is from the right, isn't it? I'm not sure why I did it that way, but we're getting, so this is the limit as x approaches 3 from the right, and you notice I'm sorry, that's approaching from the left, right? 2.9, it's coming from the left. My apologies. So this should be a negative, and it's getting huge negatively. So we've got another one of these situations. And then what happens when it's approaching 3 from the right? And I'm not sure this time. This time I'm going this way again. So as x approaches 3 from the right, we're getting a positive huge number. And you can see that on the graph. From the right, as we head to the left here and get closer to 3, it's shooting upwards. From the left, as we approach 3, it's shooting downward. Okay, so we can see, again, they obviously don't meet. So the overall limit, as x approaches 3, again, does not exist. We have disagreement up here. And I don't know, I didn't do this before, but what's the function at 3? And not that it matters, there is no limit. You can see real clearly right down here. So this one, I mean, there's no hope of a limit here. These things totally whiff again, undefined. All right. Next scenario. We just have a good old 3 over x. You can see we have a problem again. Your domain antenna should go up. X can't be 0, and that's what we're going to approach here. Okay. So we'll load up G. So it's a good old rectangular hyperbola. And you can see again as we approach from the left, as we approach 0 from the left, it's going down big time. As we approach 0 from the right, it's going up big time. And so just to summarize then, so the limit of f of x as x approaches 0 from the left, and you can see it right here, is going down big time. And as it approaches from the right, it's going up big time. So again, we've got this total not meet, the graph is not, the two branches are not meeting. So again, the limit overall Does not exist. And we've got this undefined again. So we can't go anywhere with limits on this one. All right. Let's go on to H. Now, so I should probably, yeah, except I don't have a book. I forgot to bring Chrome. What's going on here? Let me just explain. This is a piecewise function. Normally, that would be written like here. Let me just try to write it out, just from what I see here. So, what this is saying is, in normal algebra, we would write it like this. A piecewise function. And what we're saying is, the formula is x to the 6th minus 1 over x minus 1 when x is less than 1. And it's 10 when x equals 1. I see I didn't make this parenthesis long enough. And it's 11 minus 5 over x when x is greater than 1. So the old, piecewise function. You see, I lost part of my x up here when I erased. So this is the way, this just happens to be the way you write in a piecewise function, and that could have been misleading. So this is what you're really looking at, this guy. Okay, so it's a graph in 3 pieces. So let's take a look at it. This is H, or at least as good as we can. Yeah, I'm not sure you can really see what's going on here, but when x is less than 1, we've got this piece on the left going on. When x is equal to 1, we've got this isolated dot up here that's off by itself. And then when x is greater than 1, we've got this branch that goes to the right of 1. So, of course, there would be a hole, right? I hope you can, my cursor doesn't seem to be in the right place, but there would be a hole right at x equals 1. You just see dots there. That's because those are these points on a scale. So, I mean, I could have done this graph manually, but I don't have time right now. So just tried to picture it for you. So now let's look at the limits. So here we have x approaching 1 from the left. So limit as x approaches 1 from the left. And you can, except take this one out. As it's approaching 1, it looks like it's approaching 6. Do you see that? And what's the limit? Right there, we're at what? 5.99, getting real close. And as you approach 1 from the right, that's this one. The limit, the right-hand limit, also appears to be 6. You see that? We're getting real close to it. So the overall limit, as x approaches 1, is legitimately 6, because these two are in agreement. And yet, what happens what is f of 1? It's 10. You can see that right up here. So yet, this is still, even though there's a hole there, that's what the function's approaching from both sides. So again, you need to adjust. It's okay. It's okay. So even though there's a hole in the graph, the two sides are approaching the same height. That is a legitimate limit. That one, you know, a scenario this is a little bit hard to get used to. Okay, next, I. And yeah, let's see. So this is I. Let's see if we can load that one up here. So again, I'm not sure you can really get a full view of what's going on here. But, and let me come back. Let me try to rewrite this. So this piecewise, this is a piecewise function again in one, let me see, in two pieces. So what it says is f of x equals, and in the first piece, it's 3 times 6 minus x squared, and that's when x is less than or equal to 3. And the second piece is it's pi to the x power, and that's true when x is greater than 3. So we literally have two pieces here. I'm not sure you can see that real clearly. I didn't have a chance to do that one manually. But now let's take a look at the so on one side we have a parabola. You can see that. And what is this? Pi to the x. Well, pi is a constant, and you take a constant to a power, and a constant to a power like 3 to the x. That's an exponential function. Okay, so what's going on here now as we take x? Now it's kind of interesting. All this interesting stuff's going on at 3, but do you notice how the limit kind of ignores that? Because what are we doing here? We're taking the limit, and this is at the direction, you know. So you see how we're going. I mean, what are we doing here? We're finding the limit as approaches 1. So the limit as x approaches 1 from the left, and it appears to be 15. And by the way, which of these two piecewise functions are we using here? We're using the top, right? I mean, this is x is less than or equal to 3. So this is the formula we have to be using. And sure enough, if you plug in 1, what happens? 1 squared is 1, 6 minus 1 is 5, and 5 times 3 is 15. So you can see, okay, that makes some sense. What's the limit as x, I got to uncover this, and can't see it all. So what's the limit as x this time is approaching 1 from the right? Again, it appears to be 15. So this is kind of weird. We don't even, in effect, we don't even care about this bottom branch because we never got over to 3. All the interest, as you can tell from the limit here, is to 1. So again, you got to pay really close attention to the notation to see what's going on. So here's a case where, and you know, I never did show you, let's see, we probably can't see the rest of the graph. Yeah, there's the rest of the graph. Now I can see it. So when x gets over 3, there's this branch way up there. Okay, but we don't even care because we never got over the 3. We were only, you see how the value of interest for x was 1. Okay, so you really got to watch your details. Now, because the left and right hand limits agree, we could say the general limit as x approaches 1 of this function is 15. And in fact, what is f of 15? I'm sorry, what is f of 1? So here we don't have a hole. We got the left and right hand limits agreeing. We have an overall limit, and so this is This is pretty straightforward, even though we were distracted a little bit, if you will, on this problem by that second part of the function. Okay, so for this one, we're going to go strictly on Desmos. This is 3J. So let me load up 3J. Okay, so move the graph over a little bit. So here we have this function on x to the nth minus 1 over x minus 1. Now, what's really wild here is what n is completely changes this. And I've put a slider in there. So right now, you can see, first of all, we're doing the limit as x approaches 1. And from the left, it appears to be going down to what? Negative. So as x approaches 1 from the left, it appears to be negative 6. But as x approaches 1 from the right, it again appears to be negative 6. Now watch what happens when I move the slider. You see how the graph completely changes? Maybe, yeah, do you see how the graph is now totally different when n is negative 2.6? That's because what happens when you take something to a negative power? If it was a negative, it stays negative. But if it's a positive, you know what I mean? If you take a negative to an even power, then it becomes positive. And so this function actually changes wildly as n changes. So that's kind of unique. Nevertheless, the way the function is set up, it looks like the left and right hand limits agree. So we would have a limit. So the overall limit as the function approaches 1 appears to be negative 6.5-ish approximately, even though we know that when x equals 1, undefined. So here's a case where we have a hole in the graph. We have a hole in the graph, and yet the left and the right hand limits seem to be agreeing. Okay. So this is the lesson we've been doing. How we do it on time, 8:38. I don't know, does anybody, you want to throw some questions in there? I threw a lot at you today. While you're thinking about it, I'm just going to point out that where we are here on this scale is 2.2. So here's what I need you to focus on for this particular lesson, the core exercises for 2.2. So you're going to see in the book, they're going to ask you to kind of do what we did. That is, look at limits from both a little bit of an algebra view. First of all, do the left and the right hand limits agree when you make a little chart? And then if they don't agree, well, then you know we don't have an overall limit. Secondly, if they do agree, how does that compare to the actual value at that, you know, f at, and usually we were doing 1, so what's f at 1? And even if that disagrees with both limits, the limit still exists. And of course, you also know that when the limits on the two sides don't agree, we have to say that the limit does not exist. So you're going to see they're going to have you do some graphical and some chart-related things, just like I tried to lead you in the direction of today. So that's the task at hand. Again, let me throw out if you have some questions. So I will update both the notes and the video, I would say, I don't know, within the next 10 to 15 minutes. And again, I look forward to seeing you in class tomorrow. Questions? All right, I'm going to hang it up. I'm going to stop the video. Thank you for attending. I will see you tomorrow.